Space holds secrets that will shatter everything you thought you knew about our universe. Right now, floating 1 million miles from Earth, a revolutionary machine is rewriting the laws of cosmic evolution. Scientists are stunned. Their models are crumbling. What they're discovering challenges the very foundation of how galaxies form and grow. The James Webb Space Telescope isn't just another observatory. It's humanity's most ambitious attempt to peer into the forbidden depths of time itself. This extraordinary instrument serves as our cosmic archaeologist, digging through layers of starlight that have traveled across unimaginable distances to reach us. Every photon it captures carries stories from epochs when the universe was young, wild, and completely different from today. Consider the magnitude of what this golden marvel accomplishes. When you gaze at distant galaxies through Webb's eyes, you're literally looking backward through time. The light from these cosmic islands began its journey billions of years ago, when dinosaurs hadn't even appeared on Earth. By the time these ancient photons reach Webb's mirrors, they've witnessed the birth and death of countless stars, the formation of solar systems, and the slow dance of cosmic evolution. Webb's revolutionary design makes it fundamentally different from any telescope that came before. Unlike Hubble, which orbits close to Earth and battles atmospheric interference, Webb positioned itself at a special location called Lagrange Point 2. Here, Earth's gravity and the Sun's gravity balance perfectly, allowing the telescope to maintain its position with minimal fuel consumption. This cosmic sweet spot provides Webb with an unobstructed view of the universe, free from Earth's heat and light pollution. The engineering behind this achievement defies comprehension. Webb's primary mirror spans 21 feet across, nearly 3 times larger than Hubble's. But here's the mind-bending part. This massive mirror had to fold up like origami to fit inside a rocket. 18 hexagonal segments, each plated with ultra-pure gold, work together as a single perfect reflector. The precision required is staggering. Each segment must align to within billionths of a meter. Behind this giant mirror lies Webb's most crucial component, a tennis court-sized sunshield that protects the telescope from the sun's blazing heat. This shield consists of 5 layers of material thinner than human hair, yet strong enough to withstand the harsh environment of space. Without this protection, Webb's sensitive instruments would be blinded by thermal noise from our own star. The discoveries pouring in from Webb are redefining our understanding of cosmic history. Traditional theories suggested that galaxies needed hundreds of millions of years to mature after the Big Bang. They required time for primordial hydrogen to collapse into the first stars, for those stars to forge heavy elements in their cores, and for supernovae to scatter those elements across space. Only then could complex galaxies with spiral arms and organized structures begin to form. Webb obliterated these assumptions within its first few months of operation. The telescope revealed fully mature galaxies existing when the universe was barely 300 million years old, the cosmic instant after the Big Bang. These weren't primitive proto-galaxies struggling to form their first stars. Instead, Webb found sophisticated cosmic cities with organized structures, massive black holes at their centers, and stellar populations that appeared impossibly advanced for their age. The implications shake the very foundations of cosmology. If galaxies could mature this quickly in the early universe, what unknown processes were at work? Perhaps star formation was dramatically more efficient in the primordial cosmos. Maybe dark matter clumped together faster than current models predict. Or perhaps entirely new physics governed the early universe pulses and phenomena we haven't discovered yet. These ancient galaxies appear bright and massive in Webb's images, suggesting they contain billions of stars despite their youth. Some display spiral structures that should take billions of years to develop through gravitational interactions and stellar feedback. Others show signs of having already experienced multiple generations of star formation, with older stellar populations mixed alongside younger ones. The discovery forces astronomers to confront uncomfortable questions about their models. How could nature build such complex structures so quickly? What mechanisms allowed gas to cool and collapse into stars at rates far exceeding modern predictions? These galaxies seem to violate our understanding of how cosmic evolution should proceed. Webb's ability to peer this far back in time stems from its revolutionary infrared vision. As the universe expands, light from distant objects gets stretched to longer, redder wavelengths. The most ancient galaxies have their light stretched so far that it shifts from visible light into the infrared spectrum, invisible to human eyes, but perfectly suited to Webb's detectors. This infrared capability opens windows that remained closed to previous telescopes. Webb can peer through cosmic dust clouds that blocked Hubble's view, revealing star formation hidden within dusty nebulae. It can analyze the chemical composition of exoplanet atmospheres by studying how starlight filters through alien skies. Most remarkably, it can detect the thermal glow of objects cooled by billions of years of cosmic expansion. The telescope operates in an environment of unimaginable extremes. Space near Earth experiences temperature swings of hundreds of degrees as objects move in and out of sunlight. At Webb's distant location, temperatures plummet to just a few degrees above absolute zero on the telescope's shaded side. This frigid environment is crucial for Webb's infrared observations, as any heat from the telescope itself would overwhelm the faint signals from distant cosmic sources. Webb's discoveries about ancient galaxies represent just the beginning of a revolution in our understanding of cosmic evolution. Each observation reveals new puzzles, challenging astronomers to develop more sophisticated theories about how the universe developed from its primordial simplicity into the rich cosmic tapestry we observe today. The telescope continues scanning the ancient cosmos, searching for even older galaxies that might push our understanding to its breaking point. As Webb's observations accumulate, one thing becomes clear: the early universe was far more dynamic and complex than anyone imagined. The neat, orderly progression from simple to complex that dominated cosmological thinking for decades is giving way to a messier, more chaotic picture of cosmic evolution, one where galaxies could mature with shocking speed in the universe's violent youth. Imagine a barrier so thin you could tear it with your fingernail, yet so powerful it creates the most extreme temperature difference ever engineered by humanity. Webb's sunshield represents one of the most audacious engineering achievements in space exploration history, creating conditions more extreme than anywhere naturally found in our solar system. This protective barrier consists of 5 ultra-thin membranes, each no thicker than a strand of human hair. When deployed, these layers stretch across an area equivalent to a tennis court, creating a thermal fortress that defies the brutal environment of space. The sun-facing surface endures scorching temperatures exceeding 100 degrees Celsius, high enough to boil water instantly. Meanwhile, just millimeters away, on the opposite side, temperatures plummet to minus 230 degrees Celsius, making it colder than Pluto's frozen surface. This extraordinary temperature gradient isn't accidental, it's absolutely essential for Webb's revolutionary capabilities. Infrared astronomy demands detecting the faintest heat signatures from objects billions of miles away. Any thermal interference from the telescope itself would completely overwhelm these delicate signals, rendering the instrument useless. The sunshield transforms Webb into the ultimate cosmic refrigerator, allowing its sensors to operate in near-perfect thermal isolation. The deployment of this gossamer barrier required engineering precision that bordered on the impossible. Each membrane had to unfold flawlessly in the vacuum of space, stretching to exact tensions without tearing or bunching. Ground-based testing could only simulate so much. The true test came when Webb faced the unforgiving environment beyond Earth's protective atmosphere. Engineers held their collective breath as robotic systems executed maneuvers that had been rehearsed thousands of times but never performed under actual space conditions. Beyond its protective function, the sunshield enables Webb to peer through cosmic phenomena that have remained hidden for millennia. The Carina Nebula exemplifies this capability perfectly. This stellar nursery spans over 300 light-years, containing some of the most massive and luminous stars in our galaxy. Previous telescopes could only glimpse its outer regions, blocked by dense clouds of gas and dust that absorb visible light. Webb's infrared vision transforms these obstacles into transparent windows. The nebula reveals itself as a cosmic sculpture garden where titanic stars carve magnificent caverns through surrounding material. These stellar giants burn with such intensity that their radiation pressure hollows out enormous bubbles in the surrounding gas, creating structures that dwarf our entire solar system. Within these carved-out regions, new generations of stars continue forming, their birth cries detectable only through the infrared glow that Webb specializes in capturing. The nebula's appearance through Webb's sensors resembles towering cliffs and deep valleys, but these geological metaphors barely capture the true scale. Individual mountains in this cosmic landscape stretch across dozens of light years, composed entirely of glowing gas heated by nearby stellar furnaces. The interplay between creation and destruction becomes visible as older stars clear space for younger ones, driving an endless cycle of stellar evolution. Webb's journey to this observational paradise began on Christmas Day 2021, when an Ariane 5 rocket carried humanity's most expensive scientific instrument away from Earth. The launch itself lasted merely 27 minutes, but those minutes represented the culmination of decades of planning, engineering, and anticipation. Thousands of scientists and engineers watched nervously as their life's work disappeared into the darkness, knowing that the real challenges lay ahead. The telescope's destination wasn't a simple orbit around Earth like Hubble's path. Instead, Webb traveled to Lagrange Point 2, a gravitational balance point located 1.5 million kilometers away. This remote location offers several crucial advantages: permanent darkness away from Earth's thermal interference, gravitational stability that requires minimal fuel for station keeping, and an unobstructed view of the universe, without Earth or Moon blocking observations. At the heart of Webb's revolutionary capabilities lies its massive primary mirror, a golden eye spanning 6.5 meters across. This mirror collects nearly 7 times more light than Hubble's famous reflector, enabling it to detect objects so distant that their light began traveling when the universe was barely out of its infancy. However, creating such a large mirror presented seemingly insurmountable challenges. Traditional telescope mirrors are carved from single pieces of glass, polished to perfection over months or years. Webb's mirror demanded a completely different approach. Engineers divided the reflecting surface into 18 hexagonal segments, each precision manufactured from beryllium and coated with ultra-pure gold. The beryllium provides strength while remaining lightweight, while the gold coating optimizes reflection of infrared wavelengths that Webb specializes in detecting. The true engineering marvel lies in how these 18 separate pieces transform into a single perfect mirror. After deployment, each segment must align with its neighbors to tolerances measured in nanometers, meters, distances smaller than viruses, smaller than the wavelength of light itself. Robotic actuators continuously adjust each segment's position and curvature, compensating for thermal expansion, gravitational effects, and other minute disturbances that could compromise image quality. This segmented design enabled Webb to fold compactly for launch, but it introduced complexity that made engineers lose sleep for years. Every joint, every motor, every alignment mechanism became a potential failure point. The deployment sequence included over 300 individual steps, each one irreversible and critical to mission success. Unlike satellites in Earth orbit, Webb operates too far away for any possible rescue mission. Webb's capabilities extend throughout our solar system, revealing familiar objects in completely new ways. Neptune, that distant blue giant, appeared in Webb's infrared vision like never before. The planet's faint ring system, barely glimpsed by Voyager 2 decades ago, suddenly blazed with thermal radiation. Webb detected subtle variations in ring density, gravitational disturbances caused by Neptune's moons, and atmospheric phenomena invisible to optical telescopes. The telescope's first deep field image shattered expectations about the universe's hidden complexity. Astronomers selected what appeared to be empty space, the region so small that a grain of sand held at arm's length would completely cover it. Webb's patient stare revealed thousands of galaxies within this tiny cosmic window. Some appeared as delicate spirals, others as irregular smudges, and many as gravitationally distorted arcs created by intervening galaxy clusters. Each point of light in that image represents billions of stars, potentially trillions of planets, and unimaginable possibilities for life and complexity. The photograph demonstrated that wherever Webb looks, the universe overflows with hidden structure and beauty. Even the most apparently barren regions of space teem with distant galaxies, each containing cosmic histories spanning billions of years. This single image encapsulated Webb's revolutionary impact on astronomy. Previous deep space observations required weeks or months of exposure time to reveal faint objects. Webb accomplishes the same feat in hours, opening possibilities for systematic surveys that would have taken decades with earlier instruments. The telescope promises to catalogue millions of previously unknown galaxies, each one a laboratory for understanding cosmic evolution, star formation, and the fundamental processes that shaped our universe. Every engineering nightmare that could destroy a $10 billion mission somehow transformed into flawless triumph. Webb's deployment stands as perhaps the most nerve-wracking success story in space exploration history. Over 300 individual mechanisms had to function perfectly, neither motors firing once with no second chances, cables unfurling without tangling, mirrors aligning to impossible tolerances. Each component represented a potential catastrophe that could render decades of work meaningless. Engineers spent sleepless nights imagining every possible failure scenario. A single stuck latch could prevent the sunshield from deploying properly. One misfiring motor could leave mirrors permanently misaligned. A cable catching on another component could tear the delicate sunshield membranes. The telescope carried no backup systems for its most critical deployment sequences. There simply wasn't room or weight allowance for redundancy in such a precisely engineered machine. Yet against all statistical probability, every single mechanism performed flawlessly. The sunshield unfolded like a cosmic flower blooming in slow motion. Mirror segments swung into position with mechanical ballet precision. Alignment systems engaged smoothly, bringing 18 separate reflectors into perfect unity. What should have been humanity's most expensive space disaster instead became our greatest astronomical achievement. This triumph enabled Webb to revolutionize our understanding of familiar celestial neighbors. Jupiter, that striped giant we've studied for centuries, revealed completely unexpected secrets under Webb's infrared gaze. The telescope mapped atmospheric storms with unprecedented clarity, showing how heat flows through the planet's turbulent weather systems. The famous Great Red Spot appeared as a glowing thermal beacon, its internal temperature structure visible for the first time. Most remarkably, Webb captured Jupiter's auroras dancing at the polar regions with breathtaking detail. These ghostly curtains of light result from charged particles streaming along Jupiter's powerful magnetic field lines, creating displays that dwarf Earth's northern lights. Previous observations could only hint at their structure, but Webb revealed intricate patterns and dynamics that illuminate how Jupiter's magnetosphere operates. The telescope even detected Jupiter's faint ring system and several tiny moons glowing against the darkness. These observations prove that an instrument designed to peer across cosmic distances could simultaneously unlock secrets hiding in our own cosmic backyard. Jupiter suddenly appeared fresh and mysterious again, despite centuries of telescopic study. Webb's extraordinary capabilities stem partly from its mirror's unique golden coating. Each hexagonal segment gleams with an ultra-thin layer of pure gold applied with atomic precision. This coating measures only 100 nanometers thick, so thin that the entire mirror contains less gold than a typical wedding ring. Yet this microscopic film proves absolutely crucial for Webb's infrared observations. Gold reflects infrared wavelengths more efficiently than almost any other material while remaining completely immune to space's corrosive environment. The coating process required extraordinary precision. Thickness variations of just a few nanometers could compromise image quality across the entire mirror. Engineers applied this golden film using specialized vapor deposition techniques, ensuring uniform coverage across every square centimeter of reflective surface. Without this delicate golden layer, Webb couldn't detect the faintest cosmic signals or analyze exoplanet atmospheric chemistry. The mirror's iconic appearance represents far more than aesthetic beauty. It embodies the pinnacle of materials engineering applied to astronomical observation. Webb's gravitational lensing observations reveal cosmic architecture on the grandest possible scales. When the telescope observes certain galaxy clusters, it sometimes captures galaxies appearing as elegant arcs and curves rather than normal circular shapes. These distortions aren't optical illusions. They represent space itself being warped by enormous gravitational fields. Massive galaxy clusters contain so much matter, including invisible dark matter, that they literally bend space-time around themselves. Light from distant galaxies follows these curved paths, creating natural cosmic telescopes that magnify objects billions of light-years away. Webb captures these gravitational lenses with unprecedented sharpness. revealing galaxies that would otherwise remain completely undetectable. Each warped streak of light serves dual scientific purposes. First, it provides a magnified view of incredibly ancient galaxies, allowing astronomers to study star formation in the early universe. Second, the precise shape of these distortions maps the distribution of dark matter throughout the lensing cluster. This invisible substance comprises most of the universe's mass, but interacts only through gravity, making it nearly impossible to study directly. Webb's sensitivity reaches levels that boggle comprehension. Scientists frequently explain its capabilities using a striking comparison. If a single bumblebee was sitting on the lunar surface, Webb's detectors could sense its tiny heat signature from Earth. This isn't poetic exaggeration, but literal fact, demonstrating the telescope's ability to detect infrared radiation billions of times fainter than human vision can perceive. This extraordinary sensitivity results from multiple engineering achievements working together. Webb's massive mirror collects enormous amounts of light compared to smaller telescopes. Its detectors operate at temperatures just degrees above absolute zero, virtually eliminating thermal noise. The sunshield blocks all external heat sources that could interfere with observations. Combined, these systems enable Webb to detect signals so faint they would be completely invisible to any previous instrument. Such sensitivity opens the entire universe to detailed study. Galaxies at the edge of observable space become accessible targets. Exoplanet atmospheres reveal their chemical compositions through spectroscopic analysis. Even objects within our solar system display thermal features never before detected. Webb's capabilities transform astronomy from educated guessing into precise measurement across cosmic scales. Unlike Hubble, which receives regular astronaut maintenance visits, Webb operates in complete isolation at Lagrange point 2. This gravitational balance point lies 1.5 million kilometers from Earth 4 times farther than the Moon. No current spacecraft can reach this distant location for repairs or upgrades. Every component aboard Webb must function flawlessly for years without human intervention. This isolation drove engineers to design unprecedented reliability into every system. Wherever possible, they included backup components and redundant pathways. However, some mechanisms like the sunshield deployment and mirror alignment systems couldn't accommodate backups due to weight and space constraints. These single point of failure components had to work perfectly on their first and only attempt. The remote location provides crucial advantages despite the risks. Webb maintains constant orientation relative to the Sun, Earth, and Moon, keeping its sunshield properly positioned without complex maneuvering. The telescope can observe continuously without Earth blocking its view during orbital passages. The gravitationally stable environment minimizes fuel consumption, extending mission duration far beyond minimum requirements. Webb's infrared vision transformed the famous pillars of creation from shadowy silhouettes into active stellar nurseries. These towering columns of gas and dust in the Eagle Nebula became astronomical icons through Hubble's visible light images. Appearing as dark shapes against background starlight, Webb penetrated these dusty veils to reveal the stellar birth processes hidden within. Newborn stars blazed through the cosmic fog, still wrapped in the material cocoons where they formed. Jets of superheated gas streamed from young stellar objects, carving channels through surrounding dust clouds. These phenomena remained invisible to optical telescopes, but appeared clearly in Webb's infrared observations, revealing the dynamic processes that continue sculpting these cosmic monuments across millions of years. Webb transforms gravitational lensing from cosmic curiosity into humanity's most powerful magnifying glass. When colossal galaxy clusters warp space-time with their immense gravitational fields, they create natural telescopes that amplify Webb's already extraordinary capabilities. These cosmic lenses bend and stretch light from background galaxies, sometimes creating multiple mirror images of the same distant object arranged in elegant arcs around the lensing cluster. The scientific implications stagger the imagination. Webb captures lensing phenomena with unprecedented sharpness, revealing galaxies so ancient and remote they formed when the universe was barely emerging from its dark ages. These magnified targets would remain completely invisible, even to Webb's powerful mirror, without gravitational assistance. The telescope effectively sees deeper into space and further back in time than its physical specifications should theoretically allow. Each distorted galaxy image serves as a cosmic archaeology specimen, preserving evidence of star formation processes from the universe's youth. But the lensing effects themselves reveal equally important secrets about the invisible scaffolding of reality. By precisely measuring how background galaxies appear stretched and magnified, astronomers map the distribution of dark matter throughout the lensing clusters with forensic accuracy. Dark matter comprises roughly 85% of all matter in the universe, yet it interacts only through gravity, making direct detection nearly impossible. Gravitational lensing provides one of the few tools capable of revealing where this mysterious substance concentrates and how it shapes cosmic structure. Webb's exquisite lensing observations test fundamental theories about dark matter's properties and behavior, potentially revolutionizing our understanding of the cosmos's hidden architecture. These natural cosmic telescopes also enable detailed spectroscopic analysis of extremely distant galaxies. Webb can decompose their light into component wavelengths, revealing the chemical elements present, star formation rates, and even the properties of supermassive black holes at their centers. Such measurements would be completely impossible without gravitational magnification, transforming inaccessible cosmic objects into detailed laboratories for studying early universe physics. Webb's sunshield represents perhaps the most audacious origami project ever attempted. This tennis court-sized structure had to fold into a rocket fairing barely wide enough to accommodate it, then unfold flawlessly in the vacuum of space, with no possibility of human intervention. The engineering challenges seemed almost insurmountable. Massive 5 gossamer layers of Kapton film, each thinner than human hair, stretched to precise tensions across a framework larger than most buildings. The deployment sequence required mechanical choreography of unprecedented complexity. Robotic systems had to release restraints, extend support structures, and tension each membrane layer to exact specifications. Even microscopic tears or improper tensioning could compromise the entire mission. Ground testing could only approximate space conditions, leaving crucial aspects of deployment untested until Webb actually performed the maneuvers in its operational environment. The sunshield's success enables Webb to operate in thermal conditions impossible for any previous space telescope. The sun-facing surface endures temperatures exceeding 100 degrees Celsius, while the opposite side maintains temperatures around -230 degrees Celsius. This extreme gradient creates a thermal sanctuary where Webb's sensitive instruments can detect heat signatures from objects billions of light-years away without interference from their own thermal emissions. Each layer of the sunshield incorporates specialized coatings designed to reflect specific wavelengths while allowing others to pass through. This selective optical behavior fine-tunes the thermal environment, ensuring optimal operating conditions for different instrument packages. The aluminum and silicon coatings on each membrane reflect solar radiation while maintaining structural integrity across enormous temperature variations and mechanical stresses. Webb's early galaxy discoveries shattered fundamental assumptions about cosmic evolution timelines. Conventional models suggested that galaxies required at least 500 million years after the Big Bang to develop significant structure and stellar populations. These theories assumed that early star formation proceeded slowly, with multiple generations needed to produce the heavy elements necessary for complex galactic architecture. Instead, Webb detected fully formed galaxies existing just 200 million to 300 million years after the universe began, cosmic infants displaying the characteristics of mature galactic systems. These ancient objects appear surprisingly massive and luminous, containing stellar populations that seem impossible for their age. Some display organized spiral structures that conventional theory suggested should take billions of years to develop through gravitational interactions and stellar feedback processes. The discovery forces astronomers to reconsider the efficiency of early star formation. Perhaps primordial conditions allowed stars to form much more rapidly than modern processes permit. Maybe the first stellar generations were more massive than previously thought, burning brighter and producing heavy elements more quickly. Alternatively, dark matter might have clumped into galactic halos faster than current models predict, providing gravitational scaffolding for accelerated galaxy assembly. These observations also raise profound questions about the nature of the first stars. If galaxies could mature so rapidly, the initial stellar generations must have been extraordinarily efficient at converting primordial hydrogen and helium into the heavier elements required for subsequent star formation. This suggests that population 3 stars, the theorized first generation of stellar objects, might have been more massive or more numerous than astronomers previously believed possible. Webb's infrared resolution capabilities surpass even Hubble's famous sharpness in visible wavelengths. This achievement seems counterintuitive, since infrared light has longer wavelengths than visible light, which typically results in lower resolution images. However, Webb's enormous 6.5-meter mirror, combined with advanced detector technology, overcomes this fundamental limitation, producing infrared images sharper than Hubble's visible light observations. This superior resolution revolutionizes infrared astronomy across multiple research areas. Webb can resolve individual star-forming regions within distant galaxies, map the detailed structure of dusty stellar nurseries, and even distinguish atmospheric layers in exoplanets during transit observations. The telescope's ability to combine high resolution with infrared sensitivity opens research possibilities that were completely inaccessible to previous instruments. The resolution advantage proves especially valuable for studying dust-shrouded phenomena throughout the universe. Many cosmic processes occur within dense clouds of gas and dust that completely block visible light but remain transparent to infrared radiation. Webb's sharp infrared vision penetrates these barriers, revealing star formation, planetary system assembly, and galactic structure hidden from optical telescopes. Webb's stellar nursery observations transform opaque dust clouds into transparent windows, revealing cosmic birth processes. Previous telescopes could only observe the glowing surfaces of these stellar cradles, leaving their interiors mysterious and inaccessible. Webb's infrared sensors penetrate deep into these dusty regions, revealing the earliest stages of stellar evolution with unprecedented clarity. The telescope captures starlight streaming through gaps and channels in the surrounding dust, creating images that resemble cosmic cathedrals, with beams of light piercing through celestial architecture. These observations reveal young stars still embedded in their birth material, some barely beginning to shine while others already sculpting their environments through powerful stellar winds and radiation pressure. Webb's $10 billion price tag reflects the unprecedented technical challenges required to create humanity's most ambitious scientific instrument. This enormous investment funded decades of research, development, and testing to solve engineering problems that had never been attempted before. The cost encompasses not just the telescope itself, but the entire infrastructure needed to design, build, test, and operate such a complex system. Critics questioned whether such an enormous expense could be justified for a single scientific instrument. However, Webb's revolutionary discoveries validate the investment, demonstrating capabilities that exceed even optimistic pre-launch expectations. The telescope's observations are already rewriting textbooks and forcing fundamental revisions to our understanding of cosmic evolution, star formation, and planetary system development. Deep within stellar nurseries shrouded in cosmic dust, Webb witnesses the very moment stars ignite their nuclear furnaces for the first time. These cosmic birth chambers, previously hidden from human observation, reveal infant stars still wrapped in the swirling disks of material that will eventually coalesce into planetary systems. Some newborn stellar objects launch powerful jets of superheated gas that carve dramatic channels through surrounding dust clouds, creating cosmic sculptures on scales that dwarf our imagination. Webb captures these stars at their moment of nuclear awakening, the precise instant when hydrogen fusion begins burning in their cores, and they transform from gravitational contractions into true stellar objects. These observations provide unprecedented insights into stellar formation mechanisms that have remained theoretical for decades. The telescope reveals how stellar winds and radiation pressure shape surrounding material, clearing cavities while simultaneously triggering new waves of star formation in adjacent regions. The ability to penetrate these dusty veils transforms Webb from merely a deep space observer into an intimate chronicler of our own galactic neighborhood. The Milky Way contains thousands of active star-forming regions that remained largely mysterious to previous telescopes. Webb's infrared vision opens these cosmic laboratories, allowing astronomers to study stellar birth processes occurring throughout our galaxy with revolutionary detail and precision. These observations carry profound implications for understanding planetary system formation. The dusty disks surrounding newborn stars represent the raw material from which planets eventually emerge. By studying these protoplanetary environments in real time, astronomers gain crucial insights into how rocky worlds like Earth develop from cosmic debris into complex planetary systems capable of supporting life. Webb's operational timeline promises unprecedented scientific continuity. Originally designed for a 10-year mission, the telescope's extraordinarily efficient launch and precise trajectory corrections consumed far less fuel than anticipated. Mission planners now project operational capability extending beyond 20 years, potentially reaching toward 3 decades of continuous observation. This extended lifetime represents more than mere operational efficiency. It promises transformative scientific impact across multiple generations of researchers. Graduate students beginning their careers today will potentially conduct research using Webb throughout their entire professional lives. The telescope will witness cosmic phenomena that unfold over decades, tracking long-term changes in stellar evolution, galactic dynamics, and exoplanet atmospheric development. The extended mission duration enables comprehensive surveys impossible with shorter-lived instruments. Webb can systematically catalog thousands of exoplanets, monitor stellar variability across multiple cycles, and track the evolution of distant galaxies over cosmologically significant timescales. This temporal perspective will revolutionize astronomy by providing longitudinal data previously unavailable to scientific investigation. Webb's atmospheric analysis capabilities achieved immediate validation through its detection of carbon dioxide in the atmosphere of WSP-39b, a scorching gas giant orbiting a star 700 light-years distant. This achievement transcends mere technical demonstration. It represents humanity's first definitive identification of specific molecules in an alien atmosphere using spectroscopic analysis. Carbon dioxide detection proves particularly significant because this molecule plays crucial roles in planetary climate regulation and geochemical processes. On Earth, carbon dioxide cycles through atmospheric, oceanic, and biological systems, helping maintain temperatures suitable for liquid water. Its presence in exoplanet atmospheres provides important clues about atmospheric composition, temperature regulation, and potential habitability conditions. The detection technique relies on analyzing how starlight filters through planetary atmospheres during transit events. As an exoplanet passes between its host star and Webb's detectors, atmospheric molecules absorb specific wavelengths of starlight, creating distinctive spectroscopic signatures. Webb's unprecedented sensitivity and spectral resolution enable identification of individual molecular species with confidence levels impossible for previous instruments. This capability opens pathways toward detecting atmospheric biosignatures, molecular combinations that could indicate biological processes. Oxygen combined with water vapor, or methane alongside carbon dioxide, might suggest active biological systems modifying planetary atmospheres. Webb's spectroscopic precision brings such detections within realistic possibility for favorable target systems. Webb's 18-segment primary mirror required alignment, precision that pushes engineering capabilities to their absolute limits. When initially deployed, each hexagonal segment pointed in slightly different directions, creating scattered light patterns rather than focused images. Mission engineers faced the extraordinary challenge of coordinating these separate mirrors into a single, perfectly coherent optical system. The alignment process demands nanometer-scale precision-eyed adjustments, measured in distances smaller than virus particles. Each mirror segment incorporates sophisticated actuators capable of making microscopic positional corrections while maintaining structural stability across enormous temperature variations. The alignment algorithms analyze starlight patterns and iteratively adjust mirror positions until all 18 segments function as one flawless reflector. This precision engineering achievement delivers optical performance exceeding original design specifications. Webb's mirror alignment proves so accurate that image sharpness surpasses theoretical predictions, enabling observations previously considered impossible. The telescope essentially functions as the most perfectly tuned mirror system ever created by human technology. The alignment system operates continuously throughout Webb's mission, making constant micro-adjustments to compensate for thermal expansion, gravitational effects, and other minute disturbances. This active optical control maintains peak performance across all observing conditions, ensuring consistent image quality regardless of target direction or environmental factors. Webb's molecular detection capabilities extend beyond simple atmospheric analysis to mapping complex organic chemistry throughout star-forming regions. Within nebulae like Orion, the telescope identifies hydrocarbon molecules, carbon-hydrogen compounds that serve as fundamental building blocks for biological chemistry. These detections prove that organic molecular synthesis occurs naturally in cosmic environments previously considered too harsh for complex chemistry. The telescope maps spatial distributions of these organic compounds, revealing how stellar radiation and shock waves influence molecular formation and destruction processes. Some regions show rich concentrations of complex hydrocarbons, while others display simpler molecular species broken down by intense stellar energy. This chemical cartography provides unprecedented insights into how organic chemistry develops in space environments. These observations address fundamental questions about life's cosmic prevalence. If organic molecules form readily in stellar nurseries and survive long enough to incorporate into forming planetary systems, then the chemical prerequisites for life might be far more widespread than previously assumed. Webb's molecular surveys suggest that carbon-based chemistry represents a common feature of cosmic evolution, rather than a rare exception. Webb's protoplanetary disk observations capture planetary formation processes in unprecedented detail. These swirling structures around young stars represent cosmic construction sites, where dust grains gradually accumulate into planetimals, asteroids, and eventually full-sized worlds. Webb's infrared sensitivity penetrates the dusty environments that conceal these formation processes from optical telescopes. The telescope reveals intricate structures within these disks, mesocaps carved by forming planets, spiral density waves caused by gravitational interactions, and asymmetric features suggesting dynamic evolution. Some systems display evidence of giant planets already clearing orbital paths, while others show early-stage accretion processes just beginning to concentrate material into protoplanetary cores. These real-time observations of planetary system assembly provide crucial validation for theoretical models developed over decades of research. Astronomers can now test their predictions against actual observations of planets forming in distant stellar systems, refining our understanding of how planetary architectures develop and evolve. Webb's spectroscopic capabilities enable detailed atmospheric forensics on exoplanets hundreds of light-years away. By analyzing how stellar light filters through planetary atmospheres during transit events, the telescope identifies specific gases, measures their concentrations, and even determines their vertical distributions within atmospheric layers. This technique transforms distant worlds from mere points of light into detailed atmospheric laboratories. The precision of these measurements reaches extraordinary levels, detecting trace gases present at parts per million concentrations in alien atmospheres. Webb has already identified water vapor, carbon dioxide, sodium, and various atmospheric hazes on multiple exoplanets, demonstrating capabilities that seemed impossible just decades ago. Webb transforms the invisible universe into a readable map through its mastery of gravitational lensing analysis. Dark matter minds seen, that enigmatic substance comprising most of the universe's mass, yet remaining completely undetectable through electromagnetic radiation, finally reveals its hidden architecture through Webb's precise observations. When massive galaxy clusters warp space-time with their combined gravitational influence, they create cosmic magnifying glasses that bend and distort light from more distant galaxies behind them. These gravitational distortions appear as elegant arcs, rings, and stretched galaxy images that encode precise information about the invisible matter distribution within the lensing clusters. Webb's extraordinary resolution captures these lensing effects with unprecedented clarity, enabling astronomers to reconstruct detailed dark matter maps through sophisticated computational analysis. Each warped galaxy image serves as a gravitational probe, revealing the three-dimensional structure of invisible scaffolding that shapes cosmic architecture. The technique resembles cosmic archaeology, where scientists decode ancient light patterns to reconstruct the universe's hidden skeleton. Webb's lensing observations probe dark matter's behavior on scales ranging from individual galaxy clusters to vast cosmic web structures spanning hundreds of millions of light years. These measurements test fundamental physics theories about dark matter's properties, gravitational interactions, and role in cosmic evolution. Most remarkably, Webb's lensing studies reveal that dark matter doesn't distribute randomly throughout space. Instead, it forms intricate networks of filaments, nodes, and voids that guide ordinary matter's assembly into the galaxies and stars we observe today. This invisible cosmic web represents the universe's fundamental architecture, the ghostly framework that determines where galaxies form, how they cluster together, and why the observable universe displays its characteristic large-scale patterns. Webb's deployment sequence stands among the most audacious engineering achievements in space exploration history. The telescope's transformation from compact launch configuration to fully operational observatory required executing over 300 critical steps with absolute precision across several weeks. Each mechanism had to function flawlessly on its first and only attempt, with no possibility of repair or second chances. The unfolding process resembled watching a mechanical organism come to life in the vacuum of space. Solar panels extended like wings catching cosmic sunlight. The massive sunshield unfurled layer by layer, each gossamer membrane stretching to precise tensions across frameworks larger than tennis courts. Mirror segments swung into their final positions with robotic choreography, guided by algorithms that corrected for thermal expansion and gravitational effects. Engineers monitored this complex ballet from mission control, knowing that any single component failure could destroy decades of work and billions of dollars of investment. The 30-day deployment period earned the nickname 30 Days of Terror, as each successful step brought both relief and increased anticipation for the next critical milestone. Against astronomical odds, every system performed flawlessly, transforming Webb from an origami puzzle into humanity's most powerful cosmic observatory. The successful deployment validated engineering approaches that pushed technological boundaries to their absolute limits. Webb proved that extraordinarily complex robotic systems could operate reliably in deep space, opening possibilities for future missions requiring similar precision and autonomy. The telescope's flawless unfolding demonstrated that ambitious scientific goals could justify accepting calculated risks that seemed almost impossible to manage. Webb's galaxy collision observations capture cosmic violence and creation occurring simultaneously across billions of years. When galaxies encounter each other through gravitational attraction, their collision triggers spectacular displays of star formation, black hole activity, and structural transformation. These cosmic crashes unfold over hundreds of millions of years, but Webb's infrared vision reveals their immediate consequences with unprecedented clarity. During galactic mergers, gravitational forces compress vast clouds of interstellar gas, triggering intense bursts of star formation that can produce thousands of new stellar objects within relatively brief periods. The collisions also feed central supermassive black holes, which gorge on disrupted gas streams and emit powerful radiation that influences surrounding star formation processes. Webb's infrared sensors penetrate dust clouds created by these violent interactions, revealing phenomena completely hidden from optical telescopes. These observations provide crucial insights into how galaxies like our Milky Way assemble through cosmic history, rather than growing steadily through gradual accretion. Most large galaxies achieve their current masses through dramatic mergers with smaller companions. Webb's collision studies reveal the detailed physics governing these transformative events, showing how galactic architecture emerges from chaos through gravitational sculpting. The telescope's merger observations also preview our galaxy's own future. Astronomical measurements indicate that Milky Way will collide with the nearby Andromeda galaxy in approximately 4 billion years. Webb's studies of similar cosmic crashes provide detailed previews of the spectacular transformation awaiting our local galactic neighborhood, offering scientific insights with deeply personal relevance for humanity's cosmic perspective. Webb's early observations shattered established theories about galactic evolution timelines, forcing astronomers to reconsider fundamental assumptions about cosmic development. Pre-Webb models suggested that massive, organized galaxies required billions of years to assemble through gradual processes of star formation, chemical enrichment, and structural evolution. These theories assumed that early universe conditions limited the efficiency of galaxy formation processes. Instead, Webb discovered fully mature galaxies existing less than 1 billion years after the Big Bang News cosmic adolescence, displaying characteristics that conventional theory attributed only to ancient galactic systems. Some of these early galaxies appeared as large and organized as modern elliptical systems, containing stellar populations that seemed impossibly evolved for their age. These discoveries triggered intensive theoretical revision as astronomers struggled to explain how galaxies could mature so rapidly in the early universe. Perhaps primordial conditions enabled more efficient star formation than modern environments permit. Maybe dark matter clumped into galactic halos faster than current models predict. Alternatively, the first stellar generations might have been more massive and productive than previously assumed. The observations forced scientists to confront uncomfortable possibilities about gaps in their understanding of cosmic evolution. Established computer simulations that successfully reproduced modern galactic properties failed to account for Webb's early universe observations. Theorists scrambled to develop new models incorporating more efficient formation mechanisms, revised assumptions about early stellar populations, or entirely new physics governing primordial cosmic conditions. Webb's Jupiter observations transformed our understanding of the gas giant's complex ring system from theoretical knowledge into detailed observational reality. Previous telescopes could barely detect Jupiter's gossamer rings, but Webb revealed their intricate structure with stunning clarity. These delicate bands of dust particles, generated by meteoroid impacts on small inner moons, create ghostly halos around the massive planet. The telescope's infrared sensitivity revealed subtle variations in ring density, particle composition, and gravitational interactions with Jupiter's numerous satellites. Webb also captured spectacular auroral displays at Jupiter's magnetic poles, showing how charged particles from the solar wind create light shows that dwarf Earth's northern lights. These observations demonstrated that a telescope designed for cosmic archaeology could simultaneously unlock secrets within our own solar system. Webb's sensitivity reaches levels that challenge human comprehension of faint signal detection. Scientists often describe its capabilities using the analogy of detecting a single candle's heat signature from millions of kilometers away. This extraordinary sensitivity stems from combining a massive light-collecting mirror with detectors cooled to just a few degrees above absolute zero Mimiya temperatures, colder than interstellar space. This extreme sensitivity enables Webb to study phenomena completely invisible to previous instruments. The faintest galaxies in Webb's deep field images emit light levels billions of times weaker than human vision can detect. Exoplanet atmospheric analysis relies on measuring minute variations in starlight caused by molecular absorption. Star formation studies require detecting thermal signatures from objects embedded within dense dust clouds that absorb visible wavelengths. Webb's journey from conceptual dream to operational reality spanned over 3 decades of unprecedented scientific ambition and engineering determination. The initial vision emerged in the early 1990s, when astronomers recognized Hubble's limitations for studying the most distant cosmic phenomena. While Hubble revolutionized our understanding of the nearby universe, its capabilities couldn't penetrate the cosmic dark ages when the first stars and galaxies formed. The challenge seemed almost insurmountable. Creating a telescope powerful enough to observe the universe's earliest light required revolutionary approaches to every aspect of observatory design. Engineers had to invent entirely new technologies for the segmented mirror system, develop materials capable of surviving extreme space environments, and design deployment mechanisms of unprecedented complexity. Each component pushed the boundaries of what seemed physically and technically possible. Budget constraints and technical setbacks plagued the project throughout its development. Original cost estimates proved wildly optimistic, as engineers encountered challenges that demanded innovative solutions. The segmented mirror design required precision manufacturing techniques that didn't exist when the project began. The sunshield materials needed properties that pushed polymer science to its limits. Computer simulations couldn't fully predict how these complex systems would behave in the harsh environment of deep space. Timeline delays frustrated the astronomical community, As launch dates slipped repeatedly, critics questioned whether such an ambitious project could ever succeed, arguing that the technical challenges exceeded human engineering capabilities. Some suggested scaling back the mission goals or pursuing less ambitious alternatives. However, the core team persisted, driven by their vision of unlocking cosmic secrets that had remained hidden since the universe's birth. Thousands of dedicated professionals devoted their entire careers to making Webb a reality. Engineers spent decades solving problems that had never been encountered before. Scientists refined theoretical predictions about what the telescope might discover. Technicians developed manufacturing processes for components that required tolerances measured in nanometers. Their collective persistence through setbacks, redesigns, and budget crises ultimately enabled humanity's greatest astronomical achievement. Webb's early brightness measurements of distant galaxies fundamentally challenged cosmological understanding. These ancient systems appeared far more luminous than theoretical models predicted, shining with intensities that suggested much more massive and evolved stellar populations than should have been possible so early in cosmic history. Standard galaxy formation theories assumed gradual assembly processes requiring billions of years to achieve significant brightness levels. The unexpected luminosity implies that early star formation processes operated with extraordinary efficiency. Perhaps the first stellar generations burned much hotter and brighter than modern stars, converting primordial hydrogen into heavier elements at accelerated rates. Alternatively, supermassive black holes might have formed earlier than expected, contributing additional energy through accretion processes that enhanced overall galactic brightness. These observations force astronomers to reconsider fundamental assumptions about how galaxies assembled in the primordial universe. Computer simulations that successfully reproduce modern galactic properties fail to account for the rapid brightening that Webb observes. Theorists must develop new models incorporating more efficient formation mechanisms or entirely different physics governing early cosmic evolution. The brightness puzzle represents more than academic curiosity, and it suggests that our understanding of cosmic history contains significant gaps. If galaxies could achieve such luminosity so quickly after the Big Bang, what other assumptions about early universe conditions might prove incorrect? Webb's observations humble our scientific confidence, while inspiring new theoretical frameworks that could revolutionize cosmology. Webb's exoplanet discovery capabilities extend far beyond simple detection to detailed atmospheric characterization. The telescope has confirmed dozens of new worlds orbiting distant stars, using techniques ranging from direct imaging to sophisticated transit photometry. More importantly, Webb analyzes the atmospheric compositions of these alien worlds with unprecedented precision, identifying specific molecules and measuring their concentrations. Water vapor detections on multiple exoplanets demonstrate the widespread presence of this crucial ingredient for life as we know it. Carbon dioxide measurements reveal atmospheric chemistry and potential climate regulation mechanisms. Methane detections might indicate biological processes, though geological sources remain equally plausible for most current observations. These molecular inventories transform exoplanets from abstract points of light into detailed worlds with specific environmental characteristics. Webb's atmospheric studies enable comparative planetology on a cosmic scale. By analyzing dozens of different planetary atmospheres, astronomers can identify patterns that reveal how planetary systems form and evolve. Rocky planets close to their stars show different atmospheric properties than gas giants in more distant orbits. These comparisons illuminate the processes that shaped our own solar system, while revealing the incredible diversity of planetary environments throughout the galaxy. The telescope's multi-object spectroscopy capabilities revolutionize survey astronomy through unprecedented efficiency. Webb's near-infrared spectrograph can simultaneously analyze up to 100 different galaxies in a single observation, using arrays of microscopic shutters that open and close individually to select specific targets. This technological breakthrough enables comprehensive studies that would have required decades using previous instruments. Each spectrum captured by this system reveals the chemical fingerprints of distant galaxies, the elements forged in their stars and scattered through supernova explosions. Hydrogen signatures indicate ongoing star formation rates. Heavier elements like carbon, oxygen, and iron, trace the history of stellar nucleosynthesis across cosmic time. By comparing spectra from galaxies at different distances and ages, astronomers reconstruct the universe's chemical evolution from primordial simplicity to modern complexity. This multiplexed approach transforms astronomy from studying individual objects to analyzing entire populations simultaneously. Webb can map the properties of hundreds of galaxies across different cosmic epochs in single observing sessions, revealing patterns and trends that illuminate universal evolutionary processes. The technique resembles reading multiple historical documents simultaneously to understand how civilizations developed and changed over time. Webb's supernova remnant observations reveal the cosmic recycling processes that make life possible. When massive stars exhaust their nuclear fuel, they explode in spectacular supernovae that scatter their outer layers throughout surrounding space. Webb captures these stellar graveyards in exquisite detail, showing how shock waves and stellar winds sculpt the ejected material into intricate structures spanning light years. The Southern Ring Nebula exemplifies Webb's ability to reveal hidden complexity within familiar objects. Previous observations showed a simple glowing shell of gas, but Webb's infrared vision uncovered a binary star system at the nebula's heart. The fainter companion star proved to be the true architect of the structure, shedding its outer layers in successive waves that created the nebula's distinctive patterns. These stellar death scenes play crucial roles in cosmic chemical evolution. Elements heavier than hydrogen and helium can only be forged in stellar cores through nuclear fusion processes. When stars explode, they distribute these heavy elements throughout interstellar space, enriching the raw material for future generations of star and planet formation. Without this cosmic recycling, rocky planets like Earth and the complex chemistry required for life could never exist. Webb detected silicon particles suspended in alien planetary atmospheres, essentially sand clouds floating through extraterrestrial skies. These mineral grains form in high-altitude regions where temperatures and pressures allow rocky material to condense from gaseous compounds. The discovery reveals atmospheric chemistry more complex than previously imagined, with weather systems that transport solid particles across entire planetary atmospheres. These silicate clouds indicate that the building blocks of rocky worlds exist not just on solid surfaces but suspended in alien atmospheres. The particles might form through volcanic outgassing, asteroid impacts, or other geological processes that inject mineral dust into planetary atmospheres. Their presence suggests that planetary formation processes continue long after initial accretion, with ongoing exchanges between solid surfaces and gaseous envelopes. Webb's detailed observations of the Southern Ring Nebula unveiled intricate cosmic architecture that transforms our understanding of stellar death processes. The telescope revealed delicate arcs, ripples, and complex material knots spreading through space like frozen sculptures carved by stellar winds. These structures trace the final gasps of a dying star, similar to our Sun, offering an intimate preview of our solar system's distant future, when our own star exhausts its nuclear fuel and begins shedding its outer layers. The nebula's complexity emerges from the intricate dance between two stellar companions. The primary star, now a white dwarf, expelled its outer atmosphere in successive waves over thousands of years. Meanwhile, its fainter companion continued influencing the ejected material through gravitational interactions and stellar winds, sculpting the gas into the elaborate patterns Webb now reveals with unprecedented clarity. These observations provide crucial insights into how elements essential for life spread throughout the galaxy. During their final phases, stars like our Sun forge heavy elements including carbon, nitrogen, and oxygen, and their cores through nuclear fusion. When these stars die, they distribute these life-enabling materials into surrounding space, enriching the interstellar medium that will eventually form new generations of stars and planetary systems. Webb's ability to peer through the glowing gas reveals temperature variations, density structures, and chemical compositions across different regions of the nebula. Some areas show enrichment in specific elements, indicating how different nuclear processes operated within the dying star's core. Other regions display shock wave patterns where fast-moving stellar winds collide with previously ejected material, creating compression zones that might trigger future star formation. Comets represent pristine time capsules preserving materials from our solar system's birth, and Webb transforms our ability to study these ancient wanderers. When comets approach the Sun, solar heating causes their icy surfaces to sublimate, releasing streams of dust and gas that have remained virtually unchanged since the solar nebula collapsed 4.6 billion years ago. Webb's infrared sensitivity enables detailed analysis of this primordial material as it streams away from comet nuclei. Traditional observations showed comets as fuzzy, glowing objects with characteristic tails, but Webb reveals the actual composition of the particles they shed. Silicon compounds, carbon-based molecules, and various organic materials flow away from comet surfaces, creating chemical inventories of the early solar system. These substances represent the raw ingredients from which rocky planets formed, including the materials that eventually became Earth's oceans, atmosphere, and perhaps the building blocks of life itself. Webb tracks individual dust particles as they disperse through interplanetary space, some eventually reaching Earth as microscopic meteorites. By studying comet composition in real time, astronomers gain direct access to samples from the solar nebula without requiring expensive sample return missions. Each grain carries isotopic signatures and molecular structures that preserve information about conditions during planetary formation processes. The telescope's comet observations also reveal how these objects evolve as they repeatedly approach the Sun. Surface materials change through solar heating, while subsurface layers remain pristine. Webb can map temperature variations across comet surfaces, identifying regions where different volatile materials sublimate at varying rates. These measurements help scientists understand how comets lose mass over time and whether they might have delivered water and organic compounds to early Earth. Webb's golden mirror has transcended its scientific function to become a cultural icon representing humanity's quest for cosmic understanding. The 18 hexagonal segments form a distinctive honeycomb pattern spanning 6.5 meters, creating an instantly recognizable silhouette that symbolizes modern space exploration. The mirror's golden appearance results from an ultra-thin coating of pure gold optimized for infrared reflection, but the visual impact extends far beyond technical requirements. This engineering marvel appears in documentaries, educational materials, museum displays, and popular media as the face of 21st century astronomy. Children recognize Webb's distinctive appearance even before understanding its scientific purpose. The telescope joins iconic images like Saturn's rings or the Milky Way's spiral structure as symbols that capture public imagination and inspire interest in space science. The mirror's beauty demonstrates how functional design can achieve aesthetic excellence. Engineers didn't deliberately create an artistic masterpiece, yet their technical solutions produced an object of striking visual appeal. The segmented design required for folding and deployment created geometric patterns, reminiscent of natural structures like honeycomb or flower petals. The golden coating necessary for infrared optimization adds warmth and richness that makes the telescope appear almost alive. Webb's cultural impact extends beyond scientific communities to influence art, literature, and popular culture. The telescope appears in science fiction narratives, inspires artistic installations, and motivates educational programs worldwide. Its success demonstrates that ambitious scientific projects can capture public imagination while advancing human knowledge, creating lasting cultural legacies that extend far beyond technical achievements. Webb's observations of ancient galactic collisions reveal cosmic violence as a fundamental driver of galactic evolution. When the telescope peers billions of years into the past, it captures galaxies in the process of merging during the universe's turbulent youth. These cosmic crashes appear more frequent in the early universe than astronomers previously expected, suggesting that galactic growth through violent interactions represented a dominant evolutionary mechanism. During these collisions, gravitational forces distort galactic structures into spectacular tidal streams, arcs, and bridges of stars stretching across hundreds of thousands of light-years. The interactions compress vast clouds of interstellar gas, triggering intense bursts of star formation that can produce thousands of new stellar objects within relatively brief periods. Central supermassive black holes feed voraciously on disrupted gas streams, growing rapidly while emitting powerful radiation that influences surrounding star formation processes. Webb's collision observations provide direct evidence for how galaxies like our Milky Way achieved their current properties through chaotic assembly processes. Rather than growing steadily through gradual accretion, most large galaxies experience dramatic merger events that fundamentally reshaped their structure, stellar populations, and chemical compositions. These violent interactions mixed materials from different galactic components, creating the complex stellar populations observed in modern systems. The telescope captures these ancient cosmic crimes in remarkable detail, preserving evidence of galactic interactions that occurred when the universe was less than half its current age. Each warped spiral arm, stretched stellar stream, and disrupted galactic core tells part of the story about how gravitational violence sculpted the cosmic landscape we observe today. Webb's thermal mapping of icy moons in the outer solar system provides crucial reconnaissance for future astrobiology missions. By measuring surface temperatures on worlds like Europa, Enceladus, and Titan, the telescope identifies regions where subsurface oceans might approach close to the surface, or where geological activity generates detectable heat signatures. These observations help mission planners select optimal landing sites for future robotic explorers. Europa's surface shows temperature variations that might indicate areas where the underlying ocean creates thermal anomalies detectable from space. Enceladus displays heat patterns associated with its famous water geysers, where liquid water erupts through surface fractures. Titan reveals complex thermal structures related to its thick atmosphere and surface lakes of liquid hydrocarbons. Webb's rapid pace of discovery forces unprecedented updates to astronomical understanding. Within months of beginning operations, the telescope generated observations that challenged fundamental assumptions about galaxy formation, stellar evolution, and cosmic chemical enrichment. Students studying astronomy today encounter textbooks that become outdated within years rather than decades, as new Webb discoveries continuously reshape theoretical frameworks. This accelerated pace of discovery reflects Webb's revolutionary capabilities rather than gradual incremental progress. Typical of most scientific advances, the telescope doesn't just provide better images of known phenomena, but reveals entirely unexpected cosmic behaviors that demand theoretical revision. Galaxies appear more massive and mature than models predict. Star formation proceeds more efficiently than theories suggest. Planetary atmospheres display chemical complexity exceeding previous expectations. Webb's penetrating gaze into the Tarantula Nebula unveiled one of the most spectacular stellar birth scenes ever witnessed by human technology. Located 160,000 light-years away in our neighboring Large Magellanic Cloud, this colossal star-forming region represents the most active stellar nursery within our cosmic neighborhood. Previous telescopes revealed only a glowing cloud of luminous gas, but Webb's infrared vision pierced through obscuring dust to expose the hidden drama occurring within. The telescope discovered thousands of previously invisible young stars scattered throughout the nebula's vast expanse. Some stellar infants shine brilliantly as they begin their nuclear fusion processes, while others remain partially shrouded in the dusty cocoons where they formed. Webb's observations reveal stars at every stage of early development, from gravitational collapse of gas clouds to the moment nuclear fires ignite in stellar cores. Most remarkably, Webb traced how radiation and stellar winds from massive newborn stars sculpt the surrounding material into elaborate structures. These stellar giants blast away nearby gas and dust, creating expanding cavities that trigger additional star formation along their edges. The process creates a cascade of stellar birth that propagates through the nebula like cosmic wildfire, with each generation of stars preparing conditions for the next. The Tarantula Nebula's star formation rate exceeds that of our entire Milky Way galaxy, making it an extraordinary laboratory for studying how stellar populations develop. Webb's detailed mapping reveals how different stellar masses form in various regions, influenced by local gas densities, magnetic fields, and radiation environments. These observations provide crucial insights into how massive stellar clusters assemble and evolve over millions of years. Webb's discovery of faint dwarf galaxies orbiting massive galactic systems opens new chapters in understanding cosmic evolution. These diminutive stellar collections contain fewer stars than typical galaxies, but preserve crucial information about the universe's early development. Many dwarf galaxies maintain chemical compositions similar to primordial conditions, making them living fossils from cosmic antiquity. Previous telescopes lacked sufficient sensitivity to detect these faint companions around distant galactic systems. Webb's extraordinary light-gathering power reveals entire populations of dwarf satellites that remained invisible to earlier observations. These discoveries suggest that galaxy formation proceeded through hierarchical assembly, with small systems merging to create larger structures over cosmic time. The chemical compositions of dwarf galaxies provide direct windows into early cosmic conditions, unlike massive galaxies that experienced extensive chemical evolution through multiple generations of star formation. Many dwarfs preserve relatively pristine records of primordial element abundances. By studying their stellar populations, astronomers can reconstruct the nuclear processes that occurred in the universe's first stellar generations. Dwarf galaxy dynamics also constrain theories about dark matter behavior on small scales. These systems contain proportionally more dark matter than larger galaxies, making them sensitive probes of how invisible matter interacts gravitationally. Webb's observations enable detailed studies of dwarf galaxy properties that test fundamental physics theories about cosmic structure formation. Webb's operation demands thermal conditions more extreme than anywhere naturally occurring in our solar system. The telescope's infrared detectors must remain colder than -200 degrees Celsius to avoid being overwhelmed by their own thermal emissions. Achieving such temperatures requires sophisticated engineering that combines passive cooling through the massive sunshield with active refrigeration systems. The sunshield creates the initial thermal barrier by blocking heat from the sun, Earth, and Moon simultaneously. This enormous structure maintains temperature differences exceeding 300 degrees Celsius between its sun-facing and space-facing sides. Additional radiative cooling systems eliminate residual heat through carefully designed thermal pathways that vent warmth into deep space. Some of Webb's most sensitive instruments require even lower temperatures, achieved through specialized cryocoolers that actively refrigerate detectors to within a few degrees of absolute zero. These mechanical cooling systems operate continuously throughout the mission, maintaining thermal stability essential for detecting the faintest cosmic signals. The extreme cold enables Webb to distinguish genuine cosmic infrared radiation from instrumental thermal noise. Without this temperature control, the telescope's own heat would completely overwhelm the faint signals from distant galaxies, rendering astronomical observations impossible. The engineering achievement represents one of the most sophisticated thermal management systems ever deployed in space. Webb's asteroid discoveries demonstrate how revolutionary capabilities designed for cosmic archaeology can simultaneously advance solar system science. While calibrating instruments for deep space observations, astronomers noticed faint moving objects crossing the telescope's field of view. These turned out to be small asteroids in the main belt between Mars and Jupiter, many too dim for previous telescopes to detect. These discoveries highlight Webb's extraordinary sensitivity, even for relatively nearby objects. The telescope can detect thermal signatures from kilometer-sized asteroids that reflect minimal sunlight, opening new possibilities for cataloging the solar system's smallest components. Such observations help astronomers understand the size distribution and composition of leftover planesimals from solar system formation. Small asteroids preserve pristine records of conditions during planetary assembly processes. Unlike larger bodies that experience significant geological processing, these objects maintain original compositions from the solar nebula. Webb's ability to study their thermal properties and surface compositions provides direct insights into the materials that built rocky planets like Earth. The asteroid discoveries also demonstrate Webb's potential for planetary defense applications. By detecting previously unknown small asteroids, the telescope contributes to comprehensive catalogues of near-Earth objects that might pose future impact threats. While Webb's primary mission focuses on cosmic archaeology, its capabilities naturally extend to protecting humanity from cosmic hazards. Webb's gravitational lensing observations reveal cosmic optical illusions that transform our understanding of the universe's deepest regions. When massive galaxy clusters warp space-time with their enormous gravitational fields, they create natural telescopes that magnify and distort light from more distant galaxies. Webb captures these lensing effects with unprecedented clarity, revealing delicate arcs and multiple images of the same background galaxies. These cosmic mirages enable Webb to observe galaxies so distant they would otherwise remain completely invisible. The gravitational magnification effectively extends the telescope's reach deeper into space and further back in time than its physical specifications should allow. Some lensed galaxies appear as they existed just a few 100 million years after the Big Bang, providing direct observations of cosmic dawn. The lensing effects also reveal the distribution of dark matter within galaxy clusters. By precisely measuring how background galaxies appear distorted, astronomers map the invisible matter that creates the gravitational lenses. These observations test fundamental physics theories about dark matter's properties and behavior on cosmic scales. Webb's Carina Nebula images transformed a familiar astronomical target into an alien landscape that captured global imagination. The telescope revealed towering structures that resemble jagged mountain ranges glowing from internal light sources. These aren't geological formations, but cosmic sculptures carved by intense radiation and stellar winds from massive newborn stars. The nebula's apparent topography results from three-dimensional gas and dust distributions projected onto two-dimensional images. Dense regions appear as solid cliffs and peaks, while cavities cleared by stellar winds create valleys and canyons. The entire structure spans dozens of light years, with individual mountains larger than our solar system. Webb's infrared vision penetrates the dusty veils that hide star formation processes within the nebula. The telescope reveals stellar nurseries at various evolutionary stages, from initial gravitational collapse to nuclear ignition. Some regions show active star formation triggered by shock waves from nearby stellar explosions, while others display more quiescent conditions where stars form gradually over millions of years. The Carina observations demonstrate how massive stars reshape their birth environments through feedback processes. Stellar radiation heats surrounding gas, while stellar winds sweep away nearby material. These effects simultaneously suppress local star formation, while triggering new stellar birth in adjacent regions, creating complex patterns of stellar population development across the nebula. Webb's quest to uncover the universe's first supermassive black holes represents one of astronomy's most profound mysteries. These cosmic monsters, containing millions or billions of solar masses, already existed when the universe was less than 1 billion years old, an impossibly short time for such massive objects to grow through conventional feeding mechanisms. Webb possesses unprecedented capabilities to detect these primordial giants by identifying their distinctive infrared signatures as they consume surrounding material. The telescope searches for the telltale glow of hot gas spiraling into these ancient black holes, creating accretion disks that shine brilliantly across cosmic distances. These feeding processes generate characteristic spectral signatures that Webb can detect even from the most distant galaxies. By studying how these early black holes formed and evolved, astronomers hope to understand whether they emerged from direct collapse of primordial gas clouds or grew from remnants of the universe's first stellar generations. The discovery of these cosmic giants will revolutionize our understanding of how galaxies and black holes co-evolved throughout cosmic history. Supermassive black holes appear to regulate star formation in their host galaxies through complex feedback mechanisms involving jets, winds, and radiation. Understanding when and how these relationships began will illuminate fundamental processes that shape the universe's large-scale structure. Webb's detection capabilities could distinguish between competing formation theories by analyzing the properties of early black holes and their galactic environments. If primordial black holes form through direct gas collapse, they should display different characteristics than those that grew from stellar remnants. These observations will finally answer how cosmic giants emerged so rapidly, fundamentally altering our picture of early cosmic evolution. Webb's atmospheric analysis capabilities transform distant exoplanets from mysterious points of light into detailed worlds with specific environmental characteristics. The telescope detects molecular signatures by analyzing how starlight filters through planetary atmospheres during transit events. Different molecules absorb distinct wavelengths, creating spectroscopic fingerprints that reveal atmospheric compositions across interstellar distances. Water vapor detections prove particularly significant because liquid water represents a crucial requirement for life as we understand it. Webb has already identified water signatures in multiple exoplanet atmospheres, demonstrating that this essential molecule exists throughout our galactic neighborhood. Carbon dioxide measurements reveal atmospheric chemistry and potential climate regulation processes, while methane detections might indicate either geological activity or biological processes. The precision of these atmospheric measurements enables studies of increasingly Earth-like worlds. Webb can analyze the atmospheres of smaller rocky planets, bringing us closer to identifying truly habitable environments beyond our solar system. The telescope's spectroscopic capabilities could potentially detect biosignature gases, molecular combinations that strongly suggest biological activity. Each atmospheric detection represents a stepping stone toward answering humanity's most profound question: are we alone in the universe? Webb's ability to characterize alien atmospheres in such detail provides the tools necessary to identify worlds where life might exist, transforming astrobiology from speculation into observational science. Webb's mirror construction from beryllium represents a triumph of materials engineering under extreme conditions. This rare metallic element was selected specifically for its exceptional stability at cryogenic temperatures. While most materials contract, distort, or become brittle when subjected to temperatures below -200 degrees Celsius, beryllium maintains its structural integrity and dimensional precision. The 18 hexagonal mirror segments underwent years of precision manufacturing, with each surface polished to tolerances measured in nanometers. The beryllium substrates were then coated with microscopically thin layers of pure gold to optimize infrared light reflection. This golden coating, only 100 nanometers thick across the entire mirror system, enhances reflectivity while protecting the underlying beryllium from space environment degradation. The engineering challenges extended far beyond material selection. Each mirror segment had to survive violent launch accelerations, then deploy and align with unprecedented precision in the frigid vacuum of space. The beryllium construction enabled a mirror system that combines extraordinary strength with minimal weight, crucial factors for a telescope operating at humanity's technological limits. The completed mirror assembly represents the most precisely engineered reflecting surface ever created for space applications. Its ability to maintain perfect optical figure while experiencing extreme temperature variations enables Webb to capture photons that have traveled across the entire observable universe, carrying information from cosmic epochs never before accessible to human observation. Webb's discovery of dense stellar clusters in primordial galaxies provides direct evidence for how modern galactic structures assembled from smaller building blocks. These compact stellar associations appear as bright knots embedded within young galaxies observed just a few 100 million years after the Big Bang. Some astronomers theorize these clusters represent precursors to today's globular star clusters, while others suggest they might merge to form the central bulges of mature galaxies. The timing of these discoveries proves particularly significant because it demonstrates that galaxy assembly began much earlier than theoretical models predicted. These protoclusters contain tens of thousands of stars packed into regions smaller than typical globular clusters, creating stellar densities far exceeding anything observed in the modern universe. The stars burn intensely due to their close proximity and massive sizes, creating spectacular displays of stellar evolution accelerated by extreme environmental conditions. Webb's observations reveal how these stellar building blocks influenced early galactic development. The intense radiation and stellar winds from cluster stars shaped surrounding gas distributions, triggering additional star formation waves while simultaneously clearing spaces for continued structural evolution. These processes created the foundational architecture upon which modern galaxies built their complex structures over billions of years. By studying these ancient stellar clusters, astronomers gain insights into the fundamental mechanisms that transformed the early universe from relative simplicity into the rich diversity of galactic forms observed today. Each cluster represents a fossil record of conditions during cosmic dawn, preserving information about star formation processes, chemical evolution, and dynamical interactions that occurred when the universe was young and rapidly evolving. Webb's detection of unexpectedly massive early galaxies earned them the dramatic nickname universe breakers because they challenge fundamental assumptions about cosmic evolution timelines. These galactic giants appear to rival or exceed the Milky Way's mass, while existing only 300–500 million years after the Big Bang, a time frame previously considered insufficient for such massive systems to assemble. The discovery forces astronomers to reconsider basic principles governing galaxy formation efficiency. Traditional models assumed that early star formation proceeded slowly due to the lack of heavy elements needed for efficient gas cooling and stellar assembly. The presence of such massive early galaxies suggests either that these processes operated far more efficiently than expected, or that entirely unknown mechanisms accelerated galactic growth. Some researchers propose that early galaxies formed through different physical processes than those operating in the modern universe. Perhaps the first stellar generations were more massive and productive than current theory suggests. Alternatively, dark matter might have clumped more efficiently in the early universe, providing stronger gravitational scaffolding for rapid galactic assembly. These observations represent more than academic curiosities. They suggest fundamental gaps in our understanding of cosmic history. Webb's massive early galaxies force scientists to question established theoretical frameworks and develop new models that can account for such rapid galactic evolution. The telescope continues searching for even earlier examples that might push theoretical limits to breaking points. Webb's Jupiter observations reveal auroral phenomena far more dynamic and intense than previous measurements suggested. The gas giant's auroras appear as brilliant curtains of light surrounding both magnetic poles, created when charged particles from the solar wind interact with Jupiter's powerful magnetic field. These displays shine much brighter in infrared wavelengths than scientists anticipated, suggesting more complex energy transfer mechanisms than simple particle precipitation. The telescope also captured Jupiter's Gossamer ring system with unprecedented clarity, revealing structural details invisible to previous observations. These delicate bands of dust particles, created by meteoroid impacts on small inner moons, form ghostly halos around the massive planet. Webb's images show how these rings interact with Jupiter's magnetic field and radiation environment, creating complex dynamical behaviors. Webb's extraordinary mission duration promises to revolutionize astronomy across multiple generations of researchers. What began as a planned decade-long observatory may now operate for 20 years or longer, transforming from a single groundbreaking mission into a multi-generational scientific institution. Graduate students beginning their careers today could potentially conduct research using Webb throughout their entire professional lives, creating unprecedented continuity in cosmic observation and discovery. This extended timeline enables longitudinal studies impossible with shorter-lived instruments. Webb can monitor stellar evolution across decades, track changes in exoplanet atmospheres through multiple orbital periods, and observe how distant galaxies evolve over cosmologically significant timescales. The telescope will witness phenomena that unfold slowly by human standards, but rapidly in cosmic terms, providing temporal perspectives previously unavailable to astronomical research. The mission's longevity also ensures that Webb will complement future space telescopes rather than being replaced by them. Upcoming observatories will build upon Webb's discoveries while the original telescope continues generating new observations. This overlap creates synergistic opportunities where multiple cutting-edge instruments simultaneously study the same cosmic phenomena from different perspectives, multiplying scientific returns far beyond what any single telescope could achieve. Webb detects ancient galactic light that predates Earth's existence by extraordinary margins. Our planet formed approximately 4.5 billion years ago, but Webb routinely captures photons that began their cosmic journey over 13 billion years ago, all more than 10 times longer than Earth has existed. These ancient light particles carry information from cosmic epochs when the universe contained no rocky planets, no complex chemistry, and no possibility for life as we understand it. The telescope observes galaxies as they appeared during the universe's first few percent of its total history, revealing cosmic conditions during the transition from primordial simplicity to organized structure. These early galaxies shine surprisingly brightly despite their youth, packed with massive stars that formed much earlier than theoretical models predicted. Their unexpected luminosity suggests that stellar birth processes operated with remarkable efficiency during the universe's infancy. Webb's observations of these primordial systems provide direct empirical evidence for how the first cosmic structures assembled from the aftermath of the Big Bang. The telescope bridges the gap between theoretical predictions about early universe conditions and actual observations of how matter organized itself into the galaxies we observe today. Each ancient photon web represents a message from cosmic dawn, carrying information about physical processes that occurred when the universe was radically different from its current state. The expansion of space itself transforms these ancient galaxies into perfect targets for Webb's infrared sensors. As photons travel across billions of light years, cosmic expansion stretches their wavelengths from visible light into infrared radiation. This cosmological redshift makes the most distant galaxies invisible to optical telescopes like Hubble, but ideally suited for Webb's specialized detectors, creating a natural selection mechanism that reveals the universe's most ancient structures. Webb's measurements of early galactic growth rates shatter conventional assumptions about cosmic evolution timelines. The telescope reveals that primordial galaxies accumulated stellar mass at rates far exceeding theoretical predictions, with some systems apparently doubling their stellar populations within just tens of millions of years. Such rapid growth suggests fundamental processes governing star formation operated much more efficiently in the early universe than previously imagined. These accelerated growth rates force astronomers to reconsider basic principles of galactic assembly. Traditional models assume that early star formation proceeded slowly due to the absence of heavy elements needed for efficient gas cooling and stellar condensation. Webb's observations suggest either that these processes worked far more effectively than expected, or that entirely different mechanisms governed early cosmic evolution. The telescope essentially provides the first comprehensive growth charts for infant galaxies, tracking how these cosmic seeds developed into the magnificent spiral and elliptical systems that populate the modern universe. By comparing galactic properties across different cosmic epochs, astronomers can reconstruct the evolutionary pathways that transformed primordial gas clouds into organized stellar cities containing billions of stars. Webb's exoplanet atmospheric spectroscopy achieved immediate breakthroughs with its first detailed observations of JWST 96b, a gas giant orbiting a distant star. The telescope spectrum revealed not only the expected water vapor signatures, but also unexpected evidence of clouds and atmospheric hazes. Previous theoretical models had predicted clear, transparent atmospheres for such hot gas giants, but Webb discovered a far more complex reality. These atmospheric complications demonstrate the incredible diversity of exoplanet environments and the limitations of purely theoretical predictions. The hazes and clouds Webb detected likely consist of exotic materials that scatter light in complex ways, creating atmospheric opacity that affects how we interpret spectroscopic observations. This discovery immediately validated Webb's revolutionary capabilities, while highlighting how much we still need to learn about alien world characteristics. The observation represented a watershed moment for exoplanet science, proving that Webb could analyze atmospheric compositions across interstellar distances with unprecedented precision. The telescope's ability to detect water vapor, clouds, and hazes in a single spectrum demonstrated its potential for identifying habitable environments and possibly even biosignature gases in favorable target systems. Webb's chemical analysis of giant exoplanet atmospheres has created the first comprehensive library of alien atmospheric compositions. The telescope detects sodium and potassium in some worlds, carbon dioxide and methane in others, building a diverse catalogue that reveals the incredible variety of planetary environments throughout our galactic neighborhood. Each chemical fingerprint tells unique stories about atmospheric dynamics, thermal regulation, and evolutionary history. These discoveries enable comparative exoplanetology for the first time in astronomical history. Rather than studying individual worlds in isolation, astronomers can now analyze entire populations of planets simultaneously, identifying patterns that illuminate universal principles governing planetary formation and evolution. Webb transforms exoplanet science from cataloging individual discoveries to understanding systematic relationships between stellar environments and planetary characteristics. Webb's planetary nebula observations reveal the intricate beauty of stellar death, while documenting essential cosmic recycling processes. When stars like our Sun exhaust their nuclear fuel, They shed outer atmospheric layers in spectacular displays that create glowing shells of ionized gas. Webb's infrared vision penetrates these structures to reveal hidden details invisible to optical telescopes, delicate filaments, overlapping shells, and the faint companion stars that often sculpt these ethereal formations. The Southern Ring Nebula exemplifies Webb's ability to transform familiar objects into completely new scientific laboratories. The telescope uncovered complex structures that trace the dying star's final gasps, showing how stellar winds and radiation pressure create elaborate patterns in the ejected material. These observations reveal how elements forged in stellar cores might as carbon, oxygen, nitrogen, and others essential for life disperse throughout interstellar space to enrich future generations of stars and planets. Webb's sensitivity reaches levels that challenge human comprehension of faint signal detection. The telescope can register just a few photons per second from sources billions of light-years distant, operating at the theoretical limits of astronomical observation. This extraordinary capability stems from combining an enormous light-collecting mirror with detectors cooled to within degrees of absolute zero, creating an instrument capable of detecting signals billions of times fainter than human vision can perceive. This extreme sensitivity transforms astronomy by making the previously impossible routine. Galaxies too faint for any previous telescope become detailed study subjects. Exoplanet atmospheric features requiring thousands of photons for detection become accessible through patient observation. Star formation regions hidden within dense dust clouds reveal their secrets through infrared thermal emissions that penetrate obscuring material. Webb represents humanity's first true cosmic time machine and exoplanet laboratory combined into a single revolutionary instrument. No previous telescope has simultaneously possessed such powerful capabilities for studying both the universe's most ancient structures and detailed properties of nearby alien worlds. This duality creates unique scientific opportunities where cosmic archaeology and astrobiology inform each other through complementary observations and discoveries. Webb revolutionizes our understanding of cosmic architecture by revealing the hidden scaffolding that connects galaxies across vast distances. While Hubble showed us galaxies as isolated island universes scattered through space, Webb unveils the intricate cosmic web of dark matter filaments that channel galactic formation and evolution. The telescope captures young galaxies organizing themselves along these invisible highways, with star clusters forming like luminous beads strung across cosmic threads stretching hundreds of millions of light-years. These filamentary structures represent the universe's fundamental architecture, and a vast network of dark matter and gas that determines where galaxies form and how they evolve over billions of years. Webb's observations show that galactic birth and growth don't occur randomly throughout space, but follow predetermined pathways carved by gravitational forces operating since shortly after the Big Bang. Stars assemble along these cosmic rivers of matter, creating spectacular displays of coordinated stellar formation that illuminate the universe's hidden organizational principles. The telescope's ability to trace these connections transforms our perspective on galactic relationships and cosmic evolution. Instead of viewing galaxies as independent entities, Webb reveals them as components of larger structures that influence their properties, star formation rates, and evolutionary pathways. These discoveries demonstrate that understanding individual galaxies requires comprehending their positions within the cosmic web and their interactions with surrounding dark matter scaffolding. Webb's galactic observations fundamentally challenge established theories about cosmic structure formation. The telescope reveals that galaxies achieved massive sizes, complex structures, and high stellar masses much earlier than conventional models predicted. Some systems display fully developed spiral arms, organized stellar populations, and massive central bulges just a few 100 million years after the Big Bang, the characteristics that traditional theories suggested should require billions of years to develop. These discoveries force cosmologists to reconsider basic assumptions about matter, clumping efficiency, star formation rates, and galactic assembly mechanisms in the early universe. Perhaps primordial conditions enabled much more rapid stellar birth than modern environments permit. Maybe dark matter concentrated into galactic halos faster than current simulations predict. Alternatively, Entirely unknown physical processes might have accelerated cosmic evolution during the universe's youth. Webb doesn't simply answer existing questions about galactic formation meter, it reveals that our fundamental theoretical frameworks may be incomplete or incorrect. The telescope forces scientists to develop new models that can account for rapid galactic maturation, while remaining consistent with other cosmological observations. This theoretical revolution demonstrates that even our most sophisticated scientific understanding remains provisional when confronted with revolutionary observational capabilities. The implications extend beyond academic cosmology to our understanding of cosmic habitability and the potential for life throughout the universe. If galaxies matured faster than expected, then planets, chemical complexity, and potentially life itself might have emerged earlier in cosmic history than previously imagined. Webb's discoveries suggest that the universe became hospitable to complexity much sooner than traditional timelines indicated. Webb's Mars observations demonstrate the telescope's versatility for solar system science, despite its primary mission focusing on distant cosmic phenomena. From its position at Lagrange Point 2, Webb captures global snapshots of Martian atmospheric conditions with remarkable precision, detecting carbon dioxide, water vapor, and trace gases while monitoring temperature variations and dust storm dynamics across the entire planetary surface simultaneously. This global perspective provides unique advantages over spacecraft orbiting Mars or rovers, exploring local regions. Webb observes Mars as a complete system, revealing how atmospheric processes operate on planetary scales and how different regions interact through circulation patterns and weather systems. The telescope tracks seasonal changes, dust storm evolution, and atmospheric chemistry variations that require comprehensive planetary monitoring to fully understand. Webb's Martian observations prove that the telescope's extraordinary sensitivity and spectroscopic capabilities apply effectively to solar system targets, as well as cosmic archaeology. The instrument can contribute valuable data to ongoing Mars exploration efforts, while simultaneously pursuing its primary mission of studying distant galaxies and exoplanets. This dual capability maximizes scientific returns from humanity's most expensive space telescope. Webb's galactic evolutionary studies provide crucial insights into how spiral systems like our Milky Way assembled over cosmic time. By observing galaxies at different stages of development across billions of years, the telescope creates a cosmic family album showing how small proto-galaxies merged, evolved, and matured into the complex systems we observe today. These observations trace the specific processes that eventually produced our galactic home. The Milky Way's spiral structure, stellar populations, and chemical enrichment patterns all reflect its evolutionary history through mergers with smaller satellite galaxies. Webb's observations of similar processes occurring in distant systems reveal how these interactions shaped galactic properties over cosmic time. For the first time, astronomers can observe the actual precursors to Milky Way-class galaxies, watching the assembly processes that occurred billions of years before Earth formed. These discoveries provide our galaxy's origin story written across light years of space and eons of time. Webb reveals how cosmic recycling through stellar death and galactic mergers created the chemically enriched environment necessary for planet formation and life development. The telescope connects our local cosmic neighborhood to universal evolutionary processes spanning the observable universe. Webb captures stellar death processes in unprecedented detail, revealing how dying stars enrich space with elements essential for planet formation and life development. The telescope observes streams and clouds of dust, expanding from red giant stars and supernova remnants, documenting the cosmic recycling program that transforms stellar death into raw materials for future generations of cosmic structures. Red giant stars shed enormous amounts of material during their final evolutionary phases, creating expanding shells of gas, enriched with carbon, nitrogen, oxygen, and other elements forged in stellar cores through nuclear fusion. Webb's infrared sensitivity proves particularly valuable for studying these processes, since dust particles glow faintly in infrared wavelengths, while remaining invisible to optical telescopes like Hubble. The telescope tracks how stellar ejecta disperses through interstellar space, eventually becoming incorporated into molecular clouds where new stars and planetary systems form. This cosmic recycling ensures that each generation of stellar formation benefits from the nuclear ashes of previous generations, gradually increasing the universe's chemical complexity over billions of years. Webb's dust observations remind us that every atom in our bodies except hydrogen was forged in stellar cores and scattered through space by dying stars. The calcium in our bones, the iron in our blood, and the oxygen we breathe all originated in stellar furnaces that exploded billions of years ago. Webb documents these processes as they continue throughout the universe today. Webb's mirror alignment represents one of the most precise engineering achievements in human history. The 18 hexagonal segments must function as a single, perfectly smooth optical surface, with alignment tolerances measured in nanometers, Mies distances, smaller than viruses, and comparable to the width of individual molecules. This precision requires continuous micro-adjustments throughout the mission as thermal expansion, gravitational effects, and mechanical vibrations constantly threaten to disturb optimal alignment. The alignment system incorporates actuators capable of movements smaller than hydrogen atoms, enabling corrections measured in fractions of atomic diameters. These mechanisms operate continuously in the harsh environment of deep space, maintaining optical perfection across enormous temperature variations and mechanical stresses. The achievement required decades of technological development to create robotic systems capable of such extraordinary precision. Without this remarkable alignment accuracy, Webb couldn't produce the sharp images that are revolutionizing astronomy. Every breakthrough discovery depends fundamentally on maintaining optical precision that pushes engineering capabilities to their absolute limits. The mirror system stands as humanity's most delicate technological triumph, achieving mechanical perfection that defies ordinary comprehension. Webb reveals previously invisible galaxies that disappeared entirely in Hubble's observations, opening new layers of cosmic archaeology. These faint systems represent some of the earliest galactic structures ever detected, likely playing crucial roles in the retardation processes that ended the universe's dark ages. Webb doesn't simply extend Hubble's observational reach, it unveils entirely new populations of cosmic objects that remained completely inaccessible to previous technology. Each newly detected galaxy represents billions of stars that lived, evolved, and died long before our solar system formed. These ancient stellar cities preserve information about cosmic conditions during epochs, when the universe was fundamentally different from its current state. Webb's ability to detect such faint objects transforms our understanding of early cosmic structure formation and galactic evolution. Webb's near-infrared spectrograph transforms astronomical research from studying individual objects to conducting comprehensive statistical surveys of cosmic populations. This revolutionary instrument simultaneously captures spectra from up to 100 different targets, creating an observational factory that produces data at rates previously unimaginable in astronomy. Each spectrum reveals detailed information about chemical composition, temperature, motion, and evolutionary status, building vast databases that enable statistical analysis of galactic evolution across cosmic time. This multiplexed capability revolutionizes how astronomers approach fundamental questions about universe structure and evolution. Instead of spending years studying individual galaxies to understand general principles, Webb can analyze entire populations simultaneously, revealing patterns and relationships that illuminate universal processes. The instrument maps large-scale cosmic structure more efficiently than any previous telescope, creating three-dimensional surveys that trace how matter organized itself into the complex web we observe today. The spectrograph essentially converts Webb into a cosmic discovery factory, accelerating scientific progress far beyond what traditional one-object-at-a-time observations could achieve. Astronomers can now test theoretical predictions against hundreds of simultaneous measurements, rather than relying on small samples that might not represent universal behaviors. This statistical approach transforms astronomy from a largely descriptive science into one capable of rigorous quantitative analysis, comparable to laboratory physics. The instrument's efficiency enables ambitious survey programs that map cosmic evolution across billions of years. By simultaneously studying galaxies at different distances and ages, astronomers reconstruct the universe's developmental history with unprecedented detail and statistical confidence. These comprehensive datasets reveal subtle trends and correlations that remain invisible when studying isolated objects, providing insights into fundamental processes governing cosmic structure formation. Webb's massive primary mirror represents a quantum leap in light-gathering power compared to its predecessors. At 6.5 meters diameter, the telescope collects over 6 times more photons than Hubble's 2.4-meter reflector, dramatically improving sensitivity to faint cosmic phenomena. This size advantage directly translates into revolutionary observational capabilities that enable detection of previously invisible objects and phenomena throughout the universe. The mirror's collecting area determines Webb's fundamental sensitivity limits for detecting distant galaxies, analyzing exoplanet atmospheres, and studying stellar formation processes within dusty nebula. Every photon matters when observing objects billions of light years away or measuring minute atmospheric signals from transiting exoplanets. Webb's enormous mirror ensures that no cosmic whisper remains too faint to detect, opening observational territories that were completely inaccessible to previous generations of telescopes. The mirror's segmented hexagonal design enables its unprecedented size while allowing the structure to fold compactly for rocket launch. This engineering solution required developing entirely new technologies for precision alignment, thermal control, and mechanical stability under extreme space conditions. The 18 separate segments must function as a single, perfectly smooth optical surface with tolerances measured in nanometers throughout the mission duration. Without this massive light-gathering capability, Webb would be blind to the ancient galaxies and distant worlds that now populate its revolutionary images. The mirror's size enables time machine observations that peer back to cosmic dawn, while simultaneously providing the sensitivity necessary for detailed exoplanet atmospheric analysis. This dual capability makes Webb uniquely powerful for addressing fundamental questions about cosmic origins and the potential for life throughout the universe. Webb's atmospheric characterization capabilities position the telescope as humanity's most powerful tool for potentially discovering life beyond Earth. While not designed to directly detect living organisms, Webb can identify atmospheric biosignature combinations that strongly suggest biological processes. The simultaneous presence of oxygen, water vapor, and methane in rocky planet atmospheres might indicate photosynthesis, metabolism, and other biological activities similar to those occurring on Earth. The telescope's spectroscopic precision enables detection of trace gases at concentration levels that could indicate biological activity. Atmospheric oxygen represents a particularly compelling biosignature because this highly reactive gas disappears rapidly from planetary atmospheres unless continuously replenished by biological or geological processes. Combined with water vapor detections, oxygen signatures could provide strong evidence for life-sustaining environments on distant worlds. Webb's exoplanet survey capabilities will analyze dozens of potentially habitable worlds within the coming years, searching for atmospheric compositions that match theoretical predictions for life-bearing planets. The telescope can study rocky planets orbiting within stellar habitable zones where liquid water might exist on planetary surfaces. These observations could identify worlds with Earth-like atmospheric properties, bringing humanity closer to answering whether life represents a common cosmic phenomenon or a unique terrestrial accident. Each atmospheric analysis adds crucial data to humanity's understanding of planetary habitability and the potential prevalence of life throughout the galaxy. Webb's discoveries will guide future missions designed to search for life more directly, identifying the most promising targets for detailed biological investigations. The telescope serves as reconnaissance for humanity's greatest scientific quest, determining whether we are alone in the universe. Webb's observations of cosmic Webb filaments reveal the hidden architecture that governs galactic formation and evolution across the observable universe. These vast streams of gas and dark matter stretch across hundreds of millions of light years, creating scaffolding that channels matter into the galaxies we observe today. The telescope captures unprecedented images of how galaxies cluster along these cosmic highways, like luminous beads strung across invisible threads. This filamentary structure represents the universe's fundamental organizational principle, a hierarchical framework that emerged from tiny quantum fluctuations in the early universe and grew through gravitational amplification over billions of years. Webb's observations show that galactic formation doesn't occur randomly throughout space, but follows predetermined pathways carved by dark matter concentrations and gas flow patterns established shortly after the Big Bang. Understanding cosmic web architecture provides crucial insights into galaxy formation mechanisms, chemical evolution processes, and the large-scale distribution of matter throughout the universe. Galaxies residing in different environments, dense filaments versus isolated voids, display distinct properties that reflect their evolutionary histories. Webb's mapping of these structures connects local galactic characteristics to universal cosmological processes. The telescope's cosmic web observations also constrain theories about dark matter behavior and large-scale structure formation. Computer simulations predict specific patterns of filamentary organization based on different dark matter models. Webb's detailed observations test these predictions against reality, potentially revealing new physics governing how invisible matter shapes cosmic architecture on the grandest scales imaginable. Webb functions as a genuine time machine, capturing photons that began their cosmic journey over 12 billion years ago from stars that lived and died long before our solar system formed. These ancient stellar beacons burned brilliantly during the universe's youth, forging heavy elements through nuclear fusion and scattering them throughout space during spectacular supernova explosions. Their light preserves information about cosmic conditions during epochs when the universe was fundamentally different from its current state. The telescope's time machine capabilities enable direct observation of stellar evolution processes that occurred during the universe's first few billion years. Early stellar generations burned faster and died more violently than modern stars, rapidly enriching interstellar space with carbon, oxygen, silicon, and other elements essential for planet formation and life development. Webb documents these ancient stellar life cycles through the fossilized light that continues streaming across cosmic distances. Observing this prehistoric starlight allows astronomers to reconstruct the chemical evolution of the early universe with unprecedented detail. Each ancient photon carries spectroscopic fingerprints revealing the nuclear processes that operated in primordial stellar cores, the mechanisms that distributed heavy elements throughout space, and the conditions that enabled subsequent generations of stars and planets to form. Webb's data revolution forces fundamental revisions to theories about early cosmic evolution and galactic assembly processes. The telescope reveals that galaxies achieved massive sizes and complex structures far earlier than theoretical models predicted, suggesting that star formation operated with extraordinary efficiency during the universe's youth. These discoveries challenge basic assumptions about cosmic evolution timelines and the physics governing structure formation in the early universe. Webb's discovery of unexpectedly brilliant early galaxies revolutionizes our understanding of cosmic dawn by revealing a universe far more active and dynamic than theoretical predictions suggested. Astronomers anticipated detecting faint, struggling proto-galaxies during the universe's first few 100 million years, this nim collections of primitive stars barely visible even to Webb's extraordinary sensitivity. Instead, the telescope unveiled blazing stellar cities that shine with intensities rivaling mature galactic systems billions of years older. This unexpected luminosity implies that stellar birth processes operated with remarkable efficiency during the universe's infancy. Perhaps early stellar generations burned far hotter and brighter than modern stars, converting primordial hydrogen into heavier elements at accelerated rates while generating unprecedented amounts of energy. Alternatively, massive primordial black holes might have formed earlier than expected, contributing additional luminosity through violent accretion processes that heated surrounding gas to millions of degrees. Some scientists speculate that the early universe hosted exotic stellar populations, completely unlike anything observed today. The first generations of stars formed from pure hydrogen and helium, lacking the heavy elements that regulate modern stellar evolution. These population 3 stars might have achieved masses hundreds of times greater than our Sun, burning with incredible intensity before exploding in hypernovae that briefly outshone entire galaxies. Their violent deaths could have created intermediate mass black holes that continued powering galactic cores long after the original stars disappeared. Whatever mechanisms generated this ancient brilliance, Webb's observations demonstrate that cosmic dawn was anything but a gradual, quiet awakening. The early universe blazed with furious activity as matter organized itself into luminous structures with breathtaking speed. These discoveries force astronomers to completely reconsider the timeline of cosmic evolution and the physics governing structure formation during the universe's most formative epochs. Webb represents far more than a temporary scientific mission. It establishes a permanent foundation for astronomical research that will influence generations of cosmic exploration. The telescope generates data volumes so vast and information-rich that complete analysis will require decades of intensive study by researchers worldwide. Many of Hubble's most significant contributions emerged years after its initial observations, as scientists developed new analytical techniques and theoretical frameworks for interpreting archived data. Webb's scientific legacy will follow this same pattern, with discoveries continuing long after the telescope completes its active observational phase. The instrument spans the entire spectrum of cosmic questions, from fundamental cosmology and galaxy formation to exoplanet characterization and astrobiology. This breadth ensures that Webb's datasets will remain scientifically valuable across multiple research fields and theoretical developments that haven't yet been imagined. Graduate students beginning their careers today will build entire research programs around Webb's archived observations. New analytical methods will extract previously hidden information from existing datasets. Theoretical advances will provide fresh perspectives on familiar observations, revealing connections and implications that weren't apparent during initial studies. Webb's scientific impact will compound over time as researchers discover new ways to mine its rich observational heritage. The telescope's dual capabilities for studying ancient cosmic structures and contemporary exoplanetary systems create unique opportunities for connecting fundamental cosmology with astrobiology. Understanding how galaxies evolved over billions of years provides crucial context for evaluating planetary formation processes and the development of habitable environments throughout cosmic history. Webb's comprehensive approach ensures its relevance for addressing humanity's most profound scientific questions about origins, evolution, and the possibility of life beyond Earth. Webb consistently demonstrates that reality exceeds even our most ambitious theoretical expectations, revealing a universe stranger and more dynamic than scientific models predicted. From impossibly massive early galaxies to complex exoplanet atmospheres, the telescope forces astronomers to repeatedly revise fundamental assumptions about cosmic behavior. Each major discovery seems to raise more questions than it answers, highlighting the provisional nature of scientific understanding when confronted with revolutionary observational capabilities. This pattern reflects the essence of transformative science. The most important discoveries often contradict established theoretical frameworks rather than simply confirming existing knowledge. Webb reveals that the universe operates according to principles and mechanisms that remain poorly understood despite decades of theoretical development. The telescope humbles human scientific confidence while inspiring new theoretical approaches that might eventually explain its remarkable observations. The instrument's discoveries span multiple research areas simultaneously, from galaxy formation and stellar evolution to planetary science and potential astrobiology. This breadth demonstrates that cosmic phenomena interconnect in ways that transcend traditional astronomical subdisciplines. Webb's holistic approach reveals that understanding any single aspect of cosmic evolution requires comprehending its relationships to apparently unrelated processes operating across vastly different scales and timescales. Perhaps most importantly, Webb reminds us that scientific exploration remains perpetually unfinished. No matter how sophisticated our instruments become or how comprehensive our theories appear, the universe continues revealing new mysteries that challenge human understanding. The telescope stands as proof that reality always exceeds imagination, ensuring that future generations will inherit scientific frontiers as exciting and mysterious as those we explore today. Webb's iconic golden surface results from just 48 grams of pure gold, applied as an ultra-thin coating across the entire 6.5-meter mirror system. This microscopic film measures only 100 atoms thick, so thin it would be virtually invisible if peeled away from the underlying beryllium substrate. The coating's total mass roughly equals a golf ball's weight, yet this modest amount of precious metal enables observations that span the observable universe. Gold was selected not for aesthetic appeal, but for exceptional optical properties that make it ideal for infrared astronomy. The metal reflects infrared wavelengths with extraordinary efficiency while remaining completely stable in the harsh environment of deep space. Unlike other reflective materials that might tarnish, corrode, or develop surface irregularities over time, gold maintains its optical properties indefinitely under space conditions. The precision required for applying this coating challenges manufacturing capabilities to their limits. Each mirror segment underwent treatment in ultra-clean facilities where even microscopic contaminants could compromise optical performance. The gold layer was deposited atom by atom using sophisticated vacuum techniques that ensure uniform thickness across every square millimeter of reflective surface. This technological achievement transforms Webb's mirrors into extraordinarily efficient collectors of cosmic light, enabling detection of photons that have traveled across billions of light-years carrying information from the universe's most ancient epochs. The golden coating represents a perfect fusion of aesthetic beauty and functional excellence, engineering solutions that achieve visual elegance while enabling revolutionary scientific capabilities. Webb's role in guiding future astrobiology research positions the telescope as humanity's advanced scout in the search for habitable worlds beyond our solar system. By analyzing exoplanet atmospheric compositions with unprecedented precision, Webb identifies the most promising targets for detailed life detection studies by next-generation instruments. The telescope won't directly prove that life exists elsewhere, but it will dramatically narrow the search parameters for future missions. Webb's atmospheric characterization capabilities enable detection of biosignature gas combinations that might indicate biological processes. Water vapor, oxygen, methane, and carbon dioxide in specific proportions could suggest photosynthesis, metabolism, and other biological activities similar to those occurring on Earth. While geological processes might also produce some of these gases, certain molecular combinations would strongly imply biological origins. The telescope's exoplanet survey programs will analyze dozens of potentially habitable worlds during the coming years, creating comprehensive atmospheric catalogs that guide target selection for future life detection missions. This reconnaissance work ensures that subsequent instruments focus their limited observing time on the most scientifically promising candidates rather than conducting blind surveys of random planetary systems. Webb essentially establishes the foundation for humanity's greatest scientific quest, determining whether life represents a common cosmic phenomenon or a unique terrestrial accident. The telescope's discoveries will influence astrobiology research for decades, providing crucial data about planetary habitability and the prevalence of life-supporting conditions throughout our galactic neighborhood. As our journey through Webb's revolutionary discoveries draws to a gentle close, we carry with us the profound realization that this golden-mirrored sentinel has fundamentally transformed humanity's cosmic perspective. The telescope has revealed galaxies that shouldn't exist, stars wrapped in dusty cocoons of creation, and distant worlds whose skies whisper of water and exotic chemistry across the vast emptiness of space.